Welcome to today's tutorial. I'm Yingtong Huo, who's the tutor today. Today's tutorial will talk about the rest of your assignment 3 and majorly about dynamic programming. Xihui and me are responsible for this assignment 3, and we have finished grading now. We will send grades to you in a few days, and please wait for. Today, I will talk about 5 questions in your assignment, and in our grading criteria, each of these questions worth 10 points. The first question is exercise 6.4. In this exercise, we need to do the word reconstruction. Given a sequence of characters, we need to reconstruct this sequence to a sequence of valid words. And here is the algorithm. The algorithm has nested for loops over the string, which gives the big O of n squared running time. To see that the algorithm is correct, we proceed by induction on n, the length of the string. In the base case where n is equal to 0, we return true, because the empty string can be reconstituted as a valid sequence of words, and namely the empty sequence. For the inductive case, suppose t0, t1 until ti minus 1 have been correctly computed. We want to prove that the tn is also correctly computed. Simply note that tn is true just if there is some word that begins at the character sj plus 1 with the j is less than I and ends with si. And this sequence of characters before j can be also reconstituted. That is what the inner loop has done. And for the inner loop, we iterate j from I to the edge here, I here, and edge here, and we check whether this former can be reconstituted as a sequence of words and whether this can be also words. So if true, we label ti as true. And this is the algorithm for the question 1. For question boy, we modify the algorithm by adding a new table words. And the modification, you can see they're highlighted by the blue pen. These words list stores the identified words in an input sequence we've highlighted. Once a word is identified by the inner loop, and ti is true here, we also update the word list, and finally we get the result. This is all about the exercise 6.4, and most of you did the right answer. Next is the exercise 6.7. This is about the finding longest palindromic subsequences. We need to note that the palindromic subsequences is not similar to the palindromic substrings. This is because subsequences can be not continuous. For instance, you see ACGTGTCA here, the string here, and the ACGCA, ACGCA, which is not continuous, but they are also the palindromic subsequences. To solve this problem, we started from a simple case and help you better understand the algorithms and how we done. This table stores, we have a table 7 times 7 here, and the table stores the longest palindromic subsequences size. For instance, we have the string AC GT GTC. And first, we do the initialization here. For each characters A, C, G, T, respectively, itself is a palindromic subsequences of length 1. So we write 1 in the diagonal. And here in this table, I represent what the string start index, and J represent the end index. So the table T11 represent to the character A, and 1T12 represent to the string AC, and that's how the table works. So from the definition, we know that I must be smaller than J because start index is smaller than the end index. And so the lower place of the diagonal is O0 here. After we have done the initialization, we analyze when the length is 2. That means we consider two continuous characters here, AC, CG, GT, and so on. When we consider AC, we consider the length of palindromic subsequences of AC, and it is 1. So we write down 1 here. And AC, CG, GT, and so on, they are not similar, they are different. So 1 is written in every entry. After complete the length of 2, we consider the length of 3. That means we consider the 3 continuous characters. There have 5 possibilities in the string ACG GTC. That is ACG, CGT, GTG, TGT, and GTC. So similar as the last step, we see that ACG, the length of palindromic subsequences of ACG, is the longer value of AC and CG. This is because A is not equal to G. So we use the two subproblems to build a large problem. And from this table, the value of Lij is equal to the value of Lij minus 1 and Li plus 1 and J. And the process for CGT is the same as ACG. So for the example GTG, we see that the first character is exactly same as the last character. So this is a palindromic subsequences, and we use the original value plus the original value with the number of 2. That means the first and the last characters, and get the 3 here. And to sum up, we need for each of the string, each of the substring, we need to compare whether the first character is same as the last character. And if yes, we apply this formula. And if they are not same as each other, we apply this formula. And we can complete the table by this step by step. And the final result turns to the table's value in 1, 7. 1 means the start index and 7 means the end index. And this is 5. What we want is CG, TGC, and it is exactly true here. We built a 2D dimensional table L where the entry Lij stores the longest palindrome in the string from xi to the xj. Then after initialization, we apply the update formula for each of the entry. Now we write a recursive definition of Lij. If symbols xi and xj are same in this formula, we can assume that they are part of the longest palindrome. So we add 2 to their length. And Lij should be equal to Li plus 1 j minus 1 plus 2. If the two symbols are not different, so they both cannot be part of any palindrome, and the Lij's value should be the maximum value between the left part and the right part. And finally, after we finish the table, we get the L1 and 40 result. That means the string started from the index 1 and ends with the n index. Next is the cut string problems. This problem requires us to use the dynamic programming to find the minimum cost of breaking the string into n plus 1 pieces. Similar as the before exercises, we also start from a simple example. Let's illustrate this approach with this example. Suppose we have n is equal to 20 and we have 3 cuts. The cuts in position 1, position 7, and position 9. We also add the values 0 in the beginning and n plus 1 at the end. We also subtracted 1 from each internal breakpoint since we index the array started at 1 in the problem statement but 0 here. So after cutting, we have 3 cutting. We have 4 pieces. The first one is from 0 to 1, and the second one is from 2 to 7. The third one is from 8 to 9, and fourth one is from 10 to 19. This is all the preparation from our problem. We also create a table for our dynamic computation. We first enter the values I plus 1 is 0 into the table. Observe that there is no cost since the strings from 0 to 1 do not need to be broken any further. So 0, 1, 1, 2, 2, 3, and I is equal to 3, j is equal to 4. These 4 values are all 0 here. Next, we can fill the first off diagonal. Observe that there is no choice for breaking S1 for breaking these 2 pieces and these 2 pieces and these 2 pieces. Since the only breakpoint within this string is the I plus 1, so we just obtain this off diagonals. The 8 value here is because the 7 minus 0 plus 1 is equal to 8, and 9 minus 2 plus 1 is equal to 8. And in these pieces, 19 minus 8 plus 1 is equal to 12, and this is how we compute in this step. In the next, regarding the next off diagonal, there were 2 choices to break from 1 to Si to Si plus 3, that is this 3 and this 3. We have two choices, that is we break this first or break this first. So we obtain this formula. The minimum cost is the less cost from the left and less cost in the right, and add the string length itself. And we find a minimum of 2, and this is 18. We write 18 in this entry. And also T1 for its value is 27. There are two choices here, two break choices here, and we choose the order of them. In the last step, we have three choices here, and we choose the lowest cost for cutting them. And we finally get the result of 38. The minimum cost for breaking the entire string is then stored in this way. Since the table of size is m plus 1 times m plus 2 times m plus 2, and the minimum in the previous definition is taken over at most m elements. So our resulting dynamic programming algorithm has a runtime of a big O of m times m times m. And here is the formula for update elements in the table. For after initialization, this step is for initialization. After initialization, we calculate the minimum for the minimum cost for the left substring and minimum cost for the right substring, and the cost for breaking Si to Sj. This is all about exercise 66.9. And next is the problem 4. In this problem, we need to design an efficient algorithm to find the negative cycle. And if the negative cycle exists in a weighted directed graph, so we design the algorithm as below. First, we use the relaxation in Belfort algorithm for v minus 1 times. This is the same as what you need to find the shortest path in a directed graph. However, to find the negative cycle, we need to apply the relaxation for one more time. Note that if any of the shortest path has been updated in this time, we think that this is truly exists a negative cycle here, because a path length of a negative cycle will be shortened and shortened if you iterate more and more times. They will keep changing. And we also use their parent nodes to get the negative cycle. And for this question, it has 10 points, and 8 points will be given if you output whether it exists a negative cycle, and 10 points will give if you print out the negative cycle or illustrate how we can print out the negative cycle. Next is the problem 5. This problem is very similar as what you have done in your class. However, this problem requires us to find the minimum size of subset S prime from a set S of n-positive integers, so that the sum of elements in S prime is equal to W. And we also apply a simple example here to help you understand what has happened in our dynamic programming procedure. Suppose we have a set S include 4 elements 1, 2, 3, 5, and the W is equal to 8. That means we need to find a subset S prime which the number in it need sum up to 8. And we construct a dynamic table here. For simplicity, we illustrate each of the elements in S1, S2, S3, and S4 here represents as 1, 2, 3, 5 respectively. And we also use J to represent the column number. That means J is equal to 0. If J is equal to 0, we mean this column, and J is equal to 1, we means this column. Let's first do the initialization. In this initialization step, we need to compare. We iterate J from 0 to 8, and we need to compare whether S1 is equal to J. If S1 is equal to J, we write 1 here, which means the number 1 can be constituted by the number 1. And if in the else cases, we write down the infinity here. Now here it will be the infinity. And in the next step, we initialize the first column. In this column, we make them all of the value here are 0. So this entry will become 0. Eraser. Okay, so it will become to 0. This is because we can regard if W is 0, we can regard that this W0 can be constructed with 0 numbers. And note that 0 is different from the infinity number, which we will use the difference in later discussion. After initialization, we update the table by some criteria. First, let's think of the second row, that is S2. First, for this row, we also iterate J from 0 to 8. If S2 is less than J, that means J is 0 or J is 1. We just copy the value from the last row. And if S2 is equal to J, that means S2 is equal to 2. We apply 1 here. That means the number 2 can be constructed by the subset of number 2. And so on. This is quite similar with the examples you did in the class. And the difference is we use numbers to represent the size of the minimum size subset instead of the true or false here. But things happened when we consider the third row. For instance, for this entry, S3, 3, for this entry, in your class, we just need to determine the value of true or false. But here, we need to determine the minimum size. So, in this entry, if we wanted to determine the value in this entry, we need to compare the value of j minus 3, that is 0, plus 1 here, or j or the value from the last row. So this is 1 is less than 2, so we write 1 here instead of 2. In this way, it means that the number 3 can be constructed by the number 3 here, and we don't need to construct it by number 1 and number 2. We can use one element to solve the problem that is satisfying our minimum size requirement. And so forth. We can complete the whole tables. And the final result as the table is the write-down table. We can see that given W is equal to 8, we can use 1, 2, 5 to make up 8, but we also can use 3 and 5 to make up 8. And obviously, the latter one is what we want, and it has a smaller size than the first one. Here, the number is 2, and this is also corresponding to our interesting answers. Next, we need to reconstruct the subset S prime from the set S. And we started from the last entry here. We need to recognize whether this entry is computed from the last row here or here. We can clearly see that the 2 come from 1 plus 1. That is, we use 3 is equal to 1 and plus 1 get to the value of 2 here. So we add this element Si to the subset S prime. This is the first step. And in the next step, we found that this one is computed from this entry. It's 0 plus 1, so we get 1 instead of 2 in the last row. So we also add 3 to our subset S prime and get the result. So to sum up, our subset S prime has 2 integers, 3 and 5. And here is the algorithms that helps you understand. After look at the left part, we first initialize all of the tables, and after we get the table, we need to, the core operation here is we need to compare two values here, whether the value copied from the last row is smaller, or this value is smaller. And after we get the table T, we need to construct a subset S prime from the set S. And we also do the construct way. That is, we need to determine the core operation as here. That we need to determine whether this value is from the last row, copied from directly in the last row, or it is from the other way. And now we get the result here. And this question is also worth for 10 points. And if you just print true or false for this algorithm, you got 5 points. And 8 points will be given if you print out the the size of the subset as prime. That is the value of the last entry in this table. And the full point, 10 point, will give to you if you point out how to get the subset as prime. And this is all about today's tutorial. Thank you for attending and thank you for listening. If you have any questions, please type your question in the chat box or just ask me. I will give you answer as long as I can. Good luck with your rest assignment. And that's all about today. Thank you very much.